Hey, what's up guys, welcome back to Eureka, and in this video we'll be talking about the scalar product of vectors. Now, in the previous videos we talked about how we can add vectors together, subtract vectors, we discussed vector properties and all that, but we haven't really talked about multiplication. How can you multiply two vectors? Now, for numbers, there are two ways to write multiplication, right? Either, for example, 3 times 4, which is 12, obviously, or you can write 3 dot 4 is equal to 12. Those, for numbers, this cross and this dot, they're equivalent. Okay, they're the same thing. But for vectors, we need to make a distinction. Scalar product, it's also called a dot product, meaning that you take two vectors, right, vector u, dot it with vector v. Vector u cross vector v is different. They're not the same, okay? In mechanics, we won't learn about a cross product till next year, I think in grade 12, but I think this year in math, in pure mathematics, we do take the cross product. But why are there two ways to multiply two vectors, right? Because numbers, it's just multiplication. But vectors, if you think about it, multiplication of vectors, it doesn't really make sense. You can't just multiply two vectors. Adding two vectors, we kind of showed it using the triangle rule, and it makes sense. But multiplying, not so much. So multiplication of vectors, it's kind of an ambiguous idea. You don't know which one you're gonna use, dot product or cross product, but they're very different. They both kind of mean multiplication, but the ideas are really different. So what does a scalar product actually mean? Let me try to explain by drawing a coordinate axis, and I will draw two vectors. This is vector u, and then I'll draw vector v like this. This is vector v. To multiply two vectors, the idea is you take their lengths or magnitude, and then, so this is their magnitudes multiplied together, right? But what about the direction? Because if you have this vector v and that vector u, they're pointed in not opposite directions, but like closer to opposite direction than in the same direction. This is more than 90, right? If, however, you have those two vectors, they're kind of pointed in the same direction, right? So the idea is if two vectors are pointed more or less in the same direction, the dot product is just the product of the magnitudes. However, if the vectors are pointed in different directions, more than 90, their dot products should be negative. Okay, so that's the idea. To mathematically represent this idea, I'm going to write cosine of theta after this. I'm going to explain why, okay? So this is the formula for vector u dot vector v, right? And you can see that since it's just the magnitudes multiplied by each other, you can switch them around. So vector v dot vector u is equal to vector u dot vector v. Now, I haven't proven this relationship yet, but from my explanation, I hope it kind of makes sense why it's the multiplication of two vectors, the scalar product, is defined this way. Now, how does it actually look? Because I drew two vectors here, right? How can we visualize this multiplication process? If, for example, we group them differently, let's say vector u dot vector v is equal to, I'll kind of switch things around. I'll put magnitude of u times magnitude of v cosine theta. This can be represented as one thing, and then this is separate. So I'll multiply this quantity by that quantity. Alright? One remark, this theta is the angle between the two vectors. It's not the angle from the positive x-axis that rotates counterclockwise. This theta is the angle between two vectors. I'll explain why this is later, okay? But just take it as a fact for now. So, this is theta, right? Angle between two vectors. Magnitude of v cosine theta, well, we kind of recognize this as, so magnitude of v cosine theta is just the x component of the vector, right? Remember before we wrote vector v is equal to, v sub xi plus v sub yj, right? And v sub x is just magnitude of v cosine theta, and then you have an I plus magnitude of v sine theta, and then j, right? So this means that this is true, so we can, okay, what is v sub x? If we change this around somehow, I'll write cosine theta is equal to v sub x over magnitude of v, right? Cosine theta means the adjacent over hypotenuse, right? So I'll try to create a triangle. The triangle will be something like this. This will be the hypotenuse, and then this is the triangle because it has to be a right triangle, right? Because cosine is defined by the right triangle thing. Anyways, so v sub x is the adjacent. That means this right here, this length is v sub x, and of course this is the magnitude of v, right? The length of the hypotenuse is the magnitude of v. That means the green segment that I drew is v sub x, right? And vector u dot vector v is simply v sub x multiplied by magnitude of u, right? Now, what is magnitude of u? Magnitude of u is just the length of this u, right? So I'll shade it in yellow, something like this. So you see the green segment, the length of the green segment multiplied by the length of the yellow segment will be the numerical value of the scalar product. So that's how we interpret scalar products. You can basically take a vector v, right, this vector, then you project this vector onto vector u. Now, what do I mean by that? I will drop a perpendicular, dropping a perpendicular down, right, meaning I'll draw a segment from the tip of v, draw a line such that it's perpendicular to vector u, right? I'll draw a perpendicular line that will intersect u at some point. That point joined with the origin, or the tail of v, which is the origin in this case, that will be the projection of v onto u. So, as I said before, the dot product is the length of this projection, which is the red segment in this case, this red segment, multiplied by the length of the yellow segment. Now, I'm going to write something that's quite unrelated to what we've been doing right now, but I'm going to sort of redefine the scalar product. I'll say that vector u dot vector v is equal to u sub x v sub x plus u sub y v sub y, and so on if there's a z or whatever, okay? This is, if it's just written like this, that means it's two-dimensional. If it's written like you add u sub z, v sub z, this is 3D vectors, but they're the same thing, okay? Now, for most of you, this formula might be coming out of nowhere, but for the math level students, you know that if I have a row matrix U, so I have a row matrix U, this is equal to ux, not comma, sorry, uy, and then if I have a column matrix V, this is equal to vx, vy. For those of you who have no idea what this is, just ignore it, okay? If I multiply those two matrices, right, I think it's uv, you will get uxvx plus uyvy, and this is simply equals to the vector u dot product vector v, right? So this is something, it has something to do with matrices and how you can transform the coordinate axes, but I don't want to get into this, okay? This is for people who like want to know more about it, but that's it. Okay, so here's a formula that you need to know, and I'm actually going to prove what I wrote here, this formula, using this one, okay? So let's first observe a property. If I do vector u dot vector u, let's see, what will that be? It'll be ux plus uy, right? Let's just ignore the z term for now. Now this is equal to ux squared plus uy squared, right? This is vector u dot vector u. Now, what if I take the square root of this? Of course, I'll take the square root of both sides. The right-hand side will just be the magnitude of u, right? Since magnitude is defined to be the square root of the sum of the squares of their components, right? This is just the magnitude of u. So u dot u is equal to magnitude squared. I move the square root to the other side. This is the property that you need to know. If you have magnitude squared, then that is equal to the vector of that the vector dot product itself. Okay, let's start proving this formula. This one. So, remember, I think in grade 10, we learned the cosine rule or the law of cosines, right? It states that if you have a triangle, the sides are A, B, and C, and the angle, this one is angle B, this is angle C, this is angle A, right? I'm going to draw this in a similar fashion, but instead using vectors. So I'll draw this one. This is vector v. That is vector u. And what is this? This is some question mark vector, right? We don't know what this is. Now, notice that v plus this question mark vector is equal to vector u, right? That means this question mark vector is equal to u minus v. So we can replace this by u minus v. Okay, now, what does the cosine rule state? It states that choose one side, choose c. So c squared is equal to a squared plus b squared minus 2ab cosine the angle that's opposite to this side, which is big C, right? I'll also label some angles here. So this one, I'll say it's theta. This is, I don't know, alpha. This is beta. I won't use alpha and beta much. I don't think so, at least. Okay. So this is the cosine rule. You all know this, right? What if I apply the cosine rule onto this thing, this vector representation of a triangle? Now, what is C? C is the length of this side, right here. It's not the side itself. C is the length. And the length, if we're talking about vectors, is the magnitude, right? So C corresponds to vector u minus vector v. So vector u minus vector v, the magnitude of that is equal to a squared. A is the length, which is magnitude of vector v squared, length squared, I forgot the squares. B is the length, so it's the magnitude of vector u squared minus 2ab cosine c, right? 2 times vector magnitude vector v times magnitude vector u, draw this meter, vector u, cosine, what's c in this case? C is theta, and notice, theta is the angle between vector v and vector u, right? You can clearly see it right here. Now, using the property that we had before, the magnitude of a vector squared is equal to the vector dot itself, right? This means that vector u minus vector v, all this dot itself, vector u minus vector v, is equal to vector v dot vector v plus vector u dot vector u minus 2 magnitude of v magnitude of u cosine theta, right? And I haven't proved this property before, but this thing, you can distribute stuffs, okay? Stuffs, very professional. Okay, anyways, so you first have vector u dot vector u, right? So u dot u, and then you have minus v dot u. I'm just distributing minus v dot u minus v dot u again plus v dot v, right? Is equal to v dot v plus u dot u minus 2 magnitude of v magnitude of u cosine theta. Now you notice that things cancel out, right? This with that. This with that, right? Grouping those two gives us negative 2 v dot u is equal to negative 2 magnitude of v magnitude of u cosine theta. And then this negative 2 cancels out, and our result is vector v dot vector u is equal to the magnitudes multiplied by each other cosine the angle between those vectors. Now, this is the proof of the statement that I wrote here. Now, the dot product is also useful because you can test whether two vectors are perpendicular or not. If you want to test if two vectors are perpendicular, you do the dot product. Let me show you why. Vector v dot vector u is equal to, I'm just writing the formula again, cosine theta, right? If they are perpendicular, theta is 90 degrees, right? The angle between those vectors will be 90 degrees since they're perpendicular. Cosine of 90 becomes 0, right? That means if vector v is perpendicular or orthogonal, same thing, nearly same thing. If vector v is orthogonal to u, that means that v dot u will be equal to 0, right? Because cosine of theta, cosine of 90 will be equal to 0 to cancel out this whole term. So this is something that you need to know, and I think it came in the AMS this week. Now, another thing. Remember in the beginning of the video, I mentioned that if two vectors are sort of headed in the same direction, that means theta is less than 90, the dot product will be positive. If they are pointing in more or less opposite directions, meaning that theta is greater than 90, the dot product will be negative. So let me write this down. If theta, in white please, if theta is less than 90 degrees, that means v dot u will be positive. If theta is greater than 90 degrees, v dot u will be negative. And if it's equal 90 degrees, that means two vectors are orthogonal, the dot product will be 0. Those three are probably the most important things that you should remember, and you'll be using it in grade 12 a lot, like literally every single time. To end off this video, I'm going to be showing you some properties of dot products. I mentioned one before already. If we have u dot v, that will be equal to v dot u, right? This is the commutative property. The dot product is also distributive over addition. Now, what does that mean? If we have v dot u plus w, right? That means you can distribute this dot over addition. This is the addition over here. That means this will be equal to v dot u plus v dot w, right? I kind of used that property here when I got from this step to this step. Moving on, if I have a scalar into v dot u, right? That will be equal to a scalar multiple of v dot u, or v dot a scalar multiple of u. You can move that scalar around as long as they're all multiplication. So anyways guys, that should be all for this video. The formulas on this screen, they're the most important ones you should know. So make sure you know them for the exam, and if you have any questions, please leave in the comments down below, and as always, easy.